Section 5.1 is on operations with polynomials. Let's review a whole bunch of the rules about exponents. The product of powers says that x raised to the power of a times x raised to the power of b is x raised to the power of a plus b. If your bases are the same, in this case x, and you're multiplying the two powers, you add their exponents. So for example, x to the power of 2 times x to the power of 3 is x to the power of 2 plus 3, or 5. Quotient of powers, if you're dividing two powers, x to the power of a divided by x to the power of b is x to the power of a minus b. If you're dividing powers, subtract their exponents. So x to the 7th divided by x to the 3rd is x to the 4th, because 4 is 7 minus 3. Negative exponents. We're not allowed to have negative exponents. So in order to make a negative exponent positive, it needs to cross over the fraction bar. So x to the power of negative a is 1 over x to the power of positive a. If your negative a is in the denominator, you can move it to the top and make it positive. So 1 over x to the negative a is equal to x to the positive a. Here are some examples. X to the negative 7th is 1 over x to the positive 7th, and 1 over x to the negative 7th is x to the positive 7th. Basically, take the power and move it over the fraction bar, and you can make the negative exponent positive. The power of a power. So to take a power, so x to the power of a, and raise that whole thing to a power, in this case the power of b, you multiply the exponents. So x to the a, whole thing raised to the power of b, is x raised to the power of a times b. Here's an example. X to the 3rd, the whole thing raised to the 4th, is x to the 12th, because 3 times 4 is 12. The power of a product. So if I have x times y raised to the power of a, that's the same as x to the a times y to the a. An example of that would be 3x, the whole thing raised to the power of 4. That's the same thing as 3 to the 4th power times x to the 4th power. 3 to the 4th is 81, so it'd be 81 x to the 4th. Power of a quotient, so if I have x divided by y raised to the power of a, that's the same as x to the a divided by y to the a. So for example, 5/6 squared is 5 squared over 6 squared, or 25 over 36. Now, if the whole fraction, if the quotient is raised to a negative power, what you can do is flip the fraction and make the exponent positive. So x divided by y raised to the power of negative a is the same as y divided by x raised to the power of positive a. So 3/4 to the negative 3 power is the same as 4/3 to the 3rd power, or 64 over 27, because 4 to the 3rd is 64, 3 to the 3rd is 27. And our last rule, anything to the 0 power is equal to 1. So for example, 8 to the power of 0 is equal to 1. No matter what your base is, if it's raised to the 0 power, it equals 1. So a monomial is simplified if there are no powers of powers, that is, there's no parentheses. Each base appears only once, so there might be only one x in your problem, one y in your problem, one z in your problem. All fractions are in the simplest form, and there are no negative exponents. So let's try a bunch of examples here and simplify each expression. 5x cubed times y to the negative 5th times 4xy cubed. So I want to multiply my coefficients. 5 times 4 is 20. Add my exponents. X to the 3rd times x to the 1 is x to the 4th. Y to the negative 5th times y to the 3rd is y to the negative 2nd. But remember, I can't have any negative exponents. I can make that negative 2 a positive 2 if I take the whole power, including the y, and move it to the bottom, move it to the across the fraction bar. So I'd have 20 x to the 4th over y squared. I can make that negative 2 positive if I move the whole power over the fraction bar. Example number 2. a to the third n to the seventh divided by a n to the fourth. So I'll treat my a's separately, so it's basically a to the third divided by a. Subtract your exponents, that gives me a squared. N to the seventh divided by n to the fourth. Subtract your exponents, that gives me n to the third. Okay. Number 3, negative 7 x to the fifth y to the fifth z to the fourth divided by 21 x to the seventh y to the fifth z to the second. Treat this like 4 separate problems. Do your coefficients, your x's, your y's, and your z's. So doing my coefficients is going to give me like a negative 1 on top and a 3 on the bottom. If I were to simplify negative 7 over 21. I'll clean that up later because I may not want a negative 1 there. X to the fifth, x to the fifth, x to the seventh. Easier way to think about this is I have 5 x's on top. I have 7 x's on the bottom. If I cancel those 5 on the top with 5 on the bottom, I'm left with 2 on the bottom. Y to the fifth over y to the fifth cancels out. It's exactly a 1. And z to the fourth on top, z to the second on the bottom. 4 z's on top, 2 z's on the bottom. 2 on the bottom cancel with 2 on the top. And I'm left with a z squared on top. Let's clean up my final answer here. I'll put that negative out front. Z squared on top. 3x squared on the bottom. N to the fifth raised to the fourth power. Remember, exponent inside the parentheses, exponent outside the parentheses, multiply them. N to the 20th. Number 5. 5, a to the negative 7th b squared divided by a times b to the negative 6th, the whole thing to the negative 3 power. Remember the rule that says that if I have a quotient, basically a fraction, raised to a negative power, I can flip that fraction and make it a positive power. So this is going to be the same as a b to the negative 6th over 5 a to the 7th b squared, the whole thing raised to the positive 3 power. I did not change any of my exponents inside. I kept my negative 6, I kept my negative 7, those all stayed the same. The only exponent that changed was the negative 3 out here, and that's because I flipped this fraction. Now I'm going to take this 3 and apply the 3 exponent out here and apply it to everything inside. So that's going to give me a to the third, b to the negative 18th, I'll deal with that in a minute, over 5 to the third is 125, a to the negative 27, b to the 6th. Now I need to clean up some of my exponents here. If I take a negative power, a power that has a negative exponent, I can move it to the top and make it positive. If I have a power that has a negative exponent on top, I can move it to the bottom and make it positive. So what this is going to give me is I'll have an a to the third on top. Now this a to the negative 21 will move up top and become an a to the positive 21. On the bottom, my 125 stays put. My b to the 6th stays put, but this b to the negative 18th on top moves down and becomes a b to the positive 18th. Let's clean that up a little bit. That's going to give me a to the 24th, adding my exponents, over 125, b to the 24th, again adding my exponents. A polynomial is the sum or difference of monomials. So if you add or subtract a whole bunch of monomials, we call that a polynomial. It will have no negative exponents or variables in the denominator. No negative exponents, I should say, nor will it have variables in the denominator, and it will have no roots, so no square roots, no cube roots, no roots of any sort. The degree of a monomial is the sum of its exponents. So if you just have one term, one monomial, add up the exponents to find its degree. The degree of the whole polynomial is the degree of the monomial with the greatest degree. So find the degree of each monomial within the polynomial. The biggest one is the degree of the polynomial. So first of all, determine whether each expression is a polynomial, and if it is, state its degree. Number 1, we have x to the 4th minus 4 times the square root of x plus 18. Might look like a polynomial, but it has a square root in it. So no, this is not a polynomial because it has a square root. Number 2, negative 16a to the 5th plus 3/4 a squared b to the 7th. Yes, this is a polynomial. Okay, even though it has a fraction, it doesn't have any variables in the denominator. It can have a fraction as a coefficient, but no variables in the bottom of a fraction. So now let's find its degree. So the degree of this monomial right here is 5. The degree of this monomial is 2 plus 7. Remember, add your exponents, or 9. I take the greatest degree of any of the monomials, so my degree is going to be 9, because 9 is bigger than 5. And example number 3, x squared minus 3 times x to the negative 1 plus 7. This has a negative exponent. Remember, this could be written as negative 3 over x in the denominator. Can't do that, so this is not a polynomial. In order to add or subtract polynomials, we're just going to combine like terms. In order to multiply polynomials, we'll use the distributive property. So let's take a look at a couple examples here. So I have the quantity 2x cubed plus 5x minus 7 minus the whole polynomial x cubed minus 3x plus 2. Since this is subtraction, I need to make sure that I actually subtract each term of the second polynomial. It's almost as though I were distributing a negative 1. So I'm going to rewrite this. 2x cubed plus 5x minus 7, and I need to do minus x cubed minus a negative 3x, which is plus 3x, and minus 2x, or minus a 2, or minus 2. Now I can combine like terms. Use colors if you like. So there's my cubes. There's my plain old x's. And there's my plain old numbers. So I will have 2x cubed minus x cubed gives me an x cubed. 5x plus 3x gives me 8x. And negative 7 minus 2 gives me a negative 9. So the tricky thing with subtraction is to make sure that you subtract the entire second polynomial. Here we have 5xy times the quantity 2x minus y plus 6y squared times the quantity x plus 6. First thing I want to do is distribute 5xy to each of those and to 6y squared to each of those. So that's going to give me a 10 x squared y minus 5x y squared plus 6x y squared plus 36 y squared. Now I need to check and see if I have any like terms. Remember, my like terms will have exactly the same variables raised to exactly the same powers. Here I have an x squared and a y, and I don't have any other x squared y's. Here I have an x and a y squared, so I actually have one here, and this is also an x with a y squared, and this is a y squared. So I can only combine those two in the middle. So 10x squared y, and negative 5 plus 6 gives me a positive 1 xy squared plus 36 y squared. Remember, you can only combine the terms that have exactly the same variables raised to exactly the same powers. And my last example here is a binomial times a trinomial. So I have to do the distributive property. I have to take this x and multiply it by each term in the trinomial. Then I have to take this 2 and multiply it by each term in the trinomial. It's kind of like the distributive property on steroids. Let's do the x first. So x times x squared gives me x third. X times 3x gives me 3x squared. X times negative 4 gives me negative 4x. Now let's distribute the 2. 2 times x squared gives me 2x squared. 2 times 3x gives me 6x. And 2 times negative 4 gives me negative 8. Combine like terms. I only have one cubed. I have 2 that are squared. And I have 2 plain old x's, and I'm out of colors, so I'll just kind of remember my negative 8 there. So I have x cubed plus 5x squared plus 2x minus 8. And that's multiplying a binomial times a trinomial.